Hi guys, it's Mrs. Brunk here. Thanks for joining me today for Lesson 5.1, Graphing Cubic Functions. And specifically in this lesson, we're going to be focusing on cubic functions relative to the parent function x cubed. So as usual, when we learn something new, we want to make connections with something we already know how to do. Just makes it a little easier, less things to learn, right? And so we're going to focus on how graphing a cubic function is similar to graphing a quadratic function. So you know that a quadratic function has the standard form, f of x is equal to ax squared plus bx plus c, right? That's called standard form, where a, b, and c are real solutions. Real numbers, excuse me. And a cannot equal 0, because again, if the a equaled 0, then that would be 0x squared, and that term would really essentially just disappear, and that would just leave us with a linear function. You can use the basic cubic function x cubed as the parent function. So remember, that was kind of how we started looking at quadratics too. We looked at x squared, right? We're going to look at x cubed, and that's the parent function, or the most basic function for a family of cubic functions related through transformations of the graph of f of x equals x cubed. So what I did here is I completed, actually I'm going to erase the graph and I'll redo this here, is I completed a table for some values for the parent function x cubed. So the parent function, remember, always passes through the origin. We knew that from our quadratic when it was set at 0, 0 with its vertex. And so if we were to create a table with a few values for x substituted in before and after, we would plug in, say, -1 and -2, and then 1 and 2. And remember when we did that with the quadratic, it looked like this. So for x, and then this was x squared. If we plugged in -2, we square -2, we got 4. If we plugged in -1 and we squared it, we got 1. If we substitute in 0, we got 0. If we put in 1, we got 1, because 1 squared is 1, and 2 squared is 4. So we saw this repeating nature of a parabola. See how it around the vertex, the values repeated on either side. Well, that's not the case in this table, because when I cube something, that means I'm multiplying it by itself 3 times. And if you take and multiply a negative number by itself so that you have 3 factors of that, that's going to be an odd number of negatives, which is going to make your answer negative. So if I were to, but yet when you square things, of course, it's always positive or 0. If I were to substitute in -1 into x cubed, and so I cubed -1, that'd be -1 times -1 times -1, that's -1. So we're getting, instead of the repeating nature around that 0.00, we actually have opposites. So when I plot that graph, okay, so say I plot that 0, 0, which is the kind of the characteristic place where the graph crosses through if it's a parent function. And then I plotted -1, -1, that would be right here. And then -2, -8, which would be right there. And then 1, 1, and then 2, 8. Okay. I get this kind of like a, looks like basically like a parabola where the one branch has flipped down. See, it's like this branch that was over here now flipped down, and it's there. So we don't have that symmetric nature. We don't have the reflection symmetric kind of graph. We do have a rotationally symmetric. So if you were to take this branch and rotate it down here, okay, you would see that it maps on to the other half of the graph. So there's a rotational symmetry instead. And if you remember back when we talked about odd and even functions, we said that means this is an odd function. So not only does it have an odd exponent, so in that respect it's an odd function, but it also is odd in that if I were to take it and reflect it over the y-axis, rotate it around the origin, it would map onto itself. So this will be our basic shape, and then we're going to just do some transformations of it. So we'll be reviewing the transformation rules. So the domain, well, let's see, the domain of this graph is all real numbers. So you can cube anything, okay? So much like with the quadratic, you could square anything, right? So, but the range this time, so remember with quadratics, so if we had this side of the, we were looking at like that was the quadratic, right? The range was always y was greater than or equal to whatever that y coordinate of the vertex was. So whatever that lowest point that it got to. But this doesn't get to a lowest point. It doesn't get to a highest point either. It goes on up and down forever. So one end of the graph points up and keeps going forever. One end points down, goes forever. So this is going to be all real numbers for both domain and range. And actually that is characteristic of any kind of function whose highest power is odd. Going to go in opposite directions. Now the end behavior, remember with end behavior we look at, like say I'm going all the way to the right, which means I'm heading towards positive infinity for the x. That's what I'm talking about right here. So as I'm going to the right, the graph is pointing up. So that's going towards positive infinity as well. As I'm going towards the left, which is x is approaching negative infinity, the output, or the y, or f of x, is approaching negative infinity. So one end goes towards positive infinity, the other end goes towards a negative infinity. The zeros of the function. Well, remember, zeros is another way of saying the x-intercepts or the solutions or whatever. And we can see this only crosses just this one time. Now, potentially a cubic function could cross 3 times, like a quadratic can potentially cross a total of 2 times, or it could cross once or not at all, right? Cubic functions, if the more like kind of elaborate they get, there could be bends and turns so that it actually crosses 3 times. So you could have something like, it would go like this, then cross down, and then go like that. That would be more elaborate. That would be we would have more things being added or subtracted. Just like with a parabola, you know how you can shift it around? Well, this one, there would be more bends and turns. That's the maximum possible would look like that, okay? So, but this is the most basic, the parent function. Just 1, 0, it's at 0, 0, it's at 0, in other words. When the function has positive values, well, this is where the function has positive values, right over on this side of the, oops, let me circle it, over here. These are positive, right? So when x is greater than 0, it has positive values, and the next part that kind of got cut off is where's the graph have negative values, and that's going to be over here when x is less than 0. And then I believe it asks in the table, which I cut off accidentally, where is the graph increasing? And actually, when you want to know if it's increasing or decreasing, you have to read a graph from left to right. And if you do, this graph is always increasing, okay? Because going left to right, the graph would always, it takes a little bend in there, right? And some cubic graphs could, have places where it's decreasing. Like if it went like this, it'd be increasing, then decreasing, then increasing like that. But this particular one is always increasing. And so where is it decreasing? Not at all. So to complete that table. So when graphing transformations of f of x is equal to x cubed, it helps to consider the effect of the transformation on 3 reference points. I mean, we can kind of get away with just looking at 3 of these points in this table, and those are the ones that are right in the middle of the table. Now, ideally, we would use all 5 of these points if we really wanted to get the absolute best graph, but sometimes that can be cumbersome to have to find the transformation's effect on 5 points. And like with the quadratics, we usually could do it with just the vertex and a point on either side. And we're going to do the same thing here with these, except for we're going to focus on that 0, 0 is not considered the vertex, because, vertex has to be a highest or lowest point. But it's kind of like the bend. It's like the bending point, okay? It's just kind of the little kink. Sometimes I call it the kink in the graph. So we have to identify that kink in the graph that kind of like just sort of, bends through that. And then a point on either side, which the easiest one would be to take the 1 point that's before it, which is -1 when x is -1, and then when x is +1. So again, we're going to kind of target in on these 3 points right here, and we'll just do transformations to those coordinates to get our new graph. So that's going to be our strategy. So I always, again, look at this basic x cubed function. So if this was like a graph that I wanted to do a transformation on, I would just kind of create this little table where I have 0, 0, -1, -1, and 1, 1. And then I'm just going to see what is whatever I'm doing to this function going to do to affect these coordinates. So when graphing transformations of x cubed, it helps to consider the effect of the transformation on 3 reference points on the graph, -1, -1, 0, 0, and 1, 1. The table lists the 3 points and the corresponding points on the graph of g of x is equal to a times 1 over b x minus h cubed plus k. So now that looks just like vertex form for a quadratic. And the only difference is that that's a to the 3rd power instead of to the 2nd power, right? But otherwise, in that graph, you can see all the transformations or all the changes that you're making to a graph. So remember that A, this number out in front, will cause a vertical stretch or compression. It will be a stretch if it's greater than 1 and a compression if it's between 0 and 1. If it's negative, it will be a reflection over the x-axis, right? So negative out in front, it's going to flip that down. But if you think about it on this, you have one side that's already pointing up, so it would take, say, this branch right here and make it flip down like this, and it would take this side of the graph and flip it up. So reflecting over the x-axis would sort of just make it kind of cross through the other way. But if you think about it, and you did that, it's also would look the same as if when you reflected over the y-axis. See, that graph, you look at that, you can't really tell if I reflected over the y-axis over the x-axis, right? Because it could be like I'm going like this, right, over the y-axis, or it could be that I'm going like this. Like, we don't know which part goes with which original piece of the graph. So x and y reflections look the same here. So remember that the 1 over b, that really means is the b is the horizontal stretch or compression amount. And if b is a number greater than 1, then that would be, like, let's say it was 2, then that in your function would appear as a 1 over 2. So it would look like it's 1/2, but because it's actually saying it's horizontally stretching by a factor of 2. So remember, you got to think about the reciprocal of whatever is being multiplied by the x. So it's kind of a little bit counterintuitive. So if that's a 1/2, it's actually a horizontal stretch by factor 2. If instead that b was actually 1/2, it would be 1 over 1/2, which would turn into 2. So that's why when you see a 2 being multiplied by the x, it actually is a horizontal compression. So you always have to look at the reciprocal when it's being done directly to the x. So the h and the k, instead of being the coordinates of the vertex, the h and the k actually represent that kink, or in the kink in the graph, or that bending through point. So anyway, this can tell us all kinds of information about what's going on to this graph. So taking a look, this one has actually been done for us. They have the parent function already graphed on here. Here it is. That's the parent function, and it's got the coordinates that I listed in the table there. But this, let's see, this, right, hold on. Here, this is the function. And if we took a look at each little thing that's being done to it, we see that 2 that's out in front, that means the a is 2. That's a vertical stretch. So that should make that, if you kind of pulled it up vertically, it's going to make that a little bit skinnier. So it's a vertical stretch by factor 2, right? Oops. And then a translation 1 unit to the right, right? Because x lies to you. So x minus 1 would mean it's moving to the right. And then minus 1 means it's going down. So there's actually 3 things happening. It's being moved to the right and down 1. And then it's being stretched by a factor of 2. And you can see that this is the new graph right here. So how did they get those points to get that graph? Well, so first of all, we've got our parent function values right here, right? We've got these. And we're just going to take and we're going to apply a transformation rule, right? The coordinate rule for this. And so we think about anything that's being done to the x coordinate. Well, let's see. So anything that's being done to the x coordinate is going to be right in here, right? This is going to be the things that are directly done to the x. So if looking at this function, all that's being done to the x is it's moved to the right. Now when we think about moving something to the right for an x, we actually have to add 1 to it, right? Or if we want to go 1 to the right. So when we write the coordinate rule, remember, we actually write what's actually going to happen. So not what it looks like in the equation, which always kind of trips us up. So we have to say x lies to you. We know in this case, if we want to go to the right one, we have to add 1 to the x. So our coordinate rule is going to look like this. We're going to take whatever these x coordinates are over here, and we're going to add 1 to it. And then with the y, we have to take the y and multiply it by 2 because it's going to have a vertical stretch, right? And then we're going to have to subtract 1 for it. So essentially what we're going to do is take this original table, we're going to apply this coordinate rule to it, and these will be our new points. So over here I have -1, I'm going to start with that point right there. -1, if I substitute it in over here, right, it would be -1 plus 1, which makes it 0. And then I have to take this -1 and plug it in here. So 2 times -1 is -2, and then -1, so -2 minus 1 would make -3. So this point right here, -1, -1 is now at 0, -3. Okay, so that's where it's going from the original position. Now 0, 0, if I put 0, 0 in there, if I put 0 and I add 1, that's going to become 1. If I put 0 in here, that's going to be 2 times 0, which is still 0, minus 1, and that's -1. So notice that when you are actually translating that point 0, 0, or transforming, the only things that affect it are a slide, because multiplying 0 by anything is not going to change it. It's still 0, right? But adding or subtracting from 0, you actually change it. So anything that's like any slide that's happening, that will affect that point 0, 0. So that kink point will move according to whatever the translations indicate, like the left or right slides or up or down slides. So then 1, 1. So if we take 1, 1 and we substitute that in, so I plug in the 1 into this rule and this 1 into this rule, right? So the 1 in for x, the 1 in for y. 1 plus 1 is 2, and then put 1 in for the y rule. 2 times 1 is 2, minus 1 is 1. And so when I plot these points, you can see them actually on the graph here, right? You've got 0, -3, actually just got cut off the graphs right down here. 1, -1, and 2, 1. So that gives us those 3 points so that we can get that kink, and we know from there it's going to shoot upwards to the right and downwards to the left. So the process that I usually go through when I'm going to graph one of these is I may or may not actually put the parent function on the graph, but I always kind of think about the table that creates it. I just kind of, and you can write it out if you want to, or just remember that these are the key points on a cubic function: -1, -1, 0, 0, and 1, 1. And then I kind of look at what is going on in terms of the transformations, and I write that coordinate rule. So that and you can actually write it out as like an ordered pair if you want to, and then just kind of superimpose it onto the, your table there. So what I can see is happening here is what's happening to the x. So if I look in there in that parenthesis part, what's happening to the x is that's going to cause it to move 3 units to the right. So that actually means my coordinate rule is x plus 3. So when you write the coordinate rule, it's kind of nice because it looks exactly like it's supposed to look. Like I see plus 3 and I think, oh, okay, it's going to go 3 to the right. When you see it in the function itself, it's a little bit, counterintuitive. So that's why we have to have that little saying x lies to you. Now what's happening to the y is there's no slide or anything, right? All that's being done is it's being multiplied by -1/2. So I have -1/2 y. So the transformations that are going to happen here is this thing's going to be a vertical compression. I'm just going to write these down. A reflection over the x-axis. And that's the negative out in front, right? And then a slide 3 units to the right. And remember that compression was a compression of a half, right? So these are the things that we have to incorporate into our coordinate rule, which we did. And now we just have to apply them to our coordinates, right? So what we're going to do is we're going to take the x values and we're going to add 3. We're going to take the y values and we're going to multiply by -1/2. And that will kind of create these coordinates that will apply this transformation. So negative 1 plus 3 is 2. Negative 1 times negative a half is positive 1/2. If I plug 0 in, 0 plus 3 is 3, and 0 times negative 1/2 y is still 0. So like I said, only slides are going to affect that kink point on the graph. And then plug in 1 and 1. So 1 for x would be 1 plus 3, that's 4. And then 1 for y would be negative 1/2 times y would be negative 1/2. So these are going to be my new coordinates. Let's go over here and plot them. So 2 and then 1/2 over 2 and up a half. Okay, so that's going to put us right here. Over 3 and up 0. And then over 4 and down a half. So if we know what the characteristics of that graph is, it's going to go like this, right? Oops. And it's going to bend through and then go like this. So we've got those 3 points, and that's really enough. And if we look at that, does that look like that was slid 3 units to the right and then reflected and compressed? Yes, I definitely see that it looks flatter, right? It's closer to the y-axis. It slid 3 units to the right, and it's facing the opposite way. So there's that reflection over the x-axis. So again, just taking those 3 key points, applying this coordinate rule, we get those key points so that we can graph this really pretty easily just by plotting those 3 points. So let's try another one. And again, eventually you may not want to even make this table of the original coordinates, right? Because you'll know them. You're going to get to, you probably already know them now. So this one looks a little more complicated. There's a lot of stuff going on here within the parentheses. So if we kind of target what's going on in here and we create a rule, okay, it's what we're doing is we've got a 2 that's inside the parentheses, right, with the x on that plus 3. So that means if we take the reciprocal of 2, that's 1/2. We actually have a horizontal compression of a half, right? Because that's really like 2 is like saying 1 over 1/2. It's the reciprocal. And then the plus 3 is actually moving at 3 units to the left. But when we write this coordinate rule, we actually say what we mean, right? So then we're also going to be, oops, I'm sorry, I didn't mean to write. I was trying to write the coordinate rule here. I was writing the description in there, sorry. So we have a horizontal compression of a half. So that would mean, oops, we'd be multiplying the x by a half. And then we have to actually move it 3 units to the left, so we would actually, in the coordinate rule, subtract 3. So when we describe that transformation in our head, we actually write down exactly the direct thing that's going to happen to x. X is going to be multiplied by a half, and then we're going to subtract 3 from it. That'll move it 3 units to the left. And then the y, all that's going to happen to that is it's going to move up 4, right? So that would be y plus 4. So if we take this coordinate rule and we apply these x and y coordinates to that, we should get our graph. So we're going to take 1/2, whatever the x is, and then subtract 3 from it. And then we're going to take whatever the y is, and we're going to add 4. And again, if we had to write, I guess I have a space to write that description, but that description would be a horizontal compression by a half, a slide 3 to the left, and 4 up. So when we graph this, we'll see if it actually looks like the description. So taking the -1, we're going to plug -1 in here and -1 in here, right? So -1 times a half is -1/2, minus 3 is -3.5, or -3.5. If we plug -1 in for the y, -1 plus 4 is 3. So our first point is going to be at -3.5 and 3. If we plug 0 in and 0 in, 0 times a half is still 0, minus 3 is -3. And once again, that compression doesn't have any effect on that kink point. And then 0 plus 4 is 4. So that new kink point is going to go from 0, 0 to -3, 4, which is not surprising because that's the slide amount, right? So that's going to go over here to negative 3 and up 4, 1, 2, 3, 4. So that's going to be that kink point in the graph. And then finally plugging 1 in and 1. 1 for x, 1 for y. 1/2 times 1 is a half, minus 3 is negative 2.5, and then 1 plus 4 is 5. So let's plot the rest of these points. So negative 3.5 and 3. So negative 3.5, 1, 2, 3, and then negative 2.5 and 5. 1, 2, 3, 4, 5. And so this is what that graph's going to look like. It's going to bend through and look like that. So if we look at that, does it look like that was slid to the left 3 and up 4? I see that, right? I see definitely see the 3 left and up, the 3 left and up 4, right? And then horizontal compression. So if you can kind of imagine taking that original graph and kind of pressing it in, except for I think I just noticed I plotted one point a little bit off. So let's see, it would be negative 3, 4, and then it was negative 2.5 and 5. Why didn't you yell at me? I know you can't do that. You can't yell at me when I'm in a video, right? There it is. Now it definitely looks like the horizontal compression. I had plotted negative 1.5 and 5 instead of negative 2.5 and 5. But you can definitely see that if you took the original graph and kind of pressed it from left to right in, like compressed it horizontally, see that's going to make it a little bit skinnier from left to right. And it looks like the graph. So that's our process. We take whatever the transformations that are occurring, we apply a coordinate rule to it, and then just substitute our points in to get our points that were going to be on our new transformed graph. So now we're going to kind of take a look at that in a little bit in reverse. So we're going to see our transformed graph, and we're going to see if we can write the function in this sort of, I guess, vertex form. It's not technically vertex form because there's not really a vertex here, but so this is a graph of the cubic function, and it's been transformed. And the first thing I always look at is, what is the kink point, or that turning point? So I know that the h and the k here are negative 2, negative 2. So that means I could go right here where this h is, and I could put negative 2 in its place. And where I see that k, I can also put negative 2 in. Okay. And now I just got to figure out, so they're telling me it's going to be in this format, which means they're telling me there must be some sort of vertical stretch or compression that's happening. So if there's any kind of change in that way, if they give you this standard form, then they want it to be a vertical stretch or compression. Because sometimes it's hard to see if it's horizontal or vertical, right? So they'll give you the general format, kind of like when we did this with quadratics way back when. So how do we figure out what exactly that is? What is that stretch or compression vertically? Well, when I look at that, normally I go to from 0, 0, I go to the right one and up one, or to the left one and down one. But here, to go between these points, I have to go, so I'm at negative 2, but now I'm going to go to the right one, and then I'm going to go up 1, 2, 3. So I'm actually going right 1 and up 3 instead of up 1, right? So that actually is stretching that coordinate up, so it's 3 times higher, and that actually means that the A must be 3. And the same thing's happening on the left-hand side. You'd go to the left one, and normally you'd go down 1, but now we're going to go to the left one and down 1, 2, 3. Okay? So it's almost kind of like we're using an idea of slope, right? Not really slope because it's not a line, but to figure out what that stretch or compression amount is. So our new, so the turning point, if I wanted to list that out, was negative 2, right? So that makes our function be 3 times x minus negative 2, which means x plus 2 cubed minus 2. So this thing is moved 2 units to the left, 2 units down, and it's vertically stretched. Now you can see there's no a reflection or anything. It's bending the way it's supposed to. It's as going left to right. It's kind of going up on the right and down on the left, which is what's supposed to be happening. So you can tell there's been no reflection. So this is our function. This is g of x right here. Okay. So this next one, you can see they're indicating that if there's a stretch or compression, it's going to be horizontal. So the first thing we always do is identify that turning point. So that's that point in the middle. That's right there. -1, -1. So my -1, oh, sorry, not -1, +1, -1. So that means I'm going to plug in for H and K. I'm going to plug in 1 for H and -1 for K. So we've got that part of the function down. We just have to figure out what kind of horizontal stretch or compression. Well, clearly this is a stretch, because you can see it's significantly wider than it typically is, right? Stretched out. So when I look at, to go from that kink point to the next point, I usually go up 1. I usually go right 1 and up 1, right? But instead I have to go 1, 2, 3, 4 to the right and up 1. So because I'm having to go 4 times as further to the right than I normally do, which is I'm usually going 1 to the right and 1 up. Now I'm going 4 to the right and up 1. I know that that stretch amount is actually 4. So I'm going to take that 4, and that's going to go in place of the B, right? It's going to go in for B. So that's actually going to make that 1/4. Okay, that's why when I write my functions like that, that 1/4 really means it's a horizontal stretch, okay, by factor 4. So wrapping this up and writing my function would look like this. It's going to be in parentheses 1/4, okay? Again, that's where the 4 comes from, because I had to go 4 to the right and then go up 1 to get that. And then x minus 1 cubed and then -1. So again, we put the turning point in, and we figured out that there was a stretch horizontally of factor 4, which makes that 1/b be 1/4. And that's our function. And you can see also that there is no reflection, right? It's still pointing up on this end and down on the other, so we know there hasn't been any kind of reflection. So now we kind of know how to go about this from both angles. So we know if we're given the equation for the function, that is the transformed equivalent to x cubed, we can figure out coordinates to create the graph. Or in the reverse, if we have points on this graph, we can turn around by looking for key information like the turning point. And then using that idea of these key points, we can figure out if something has been stretched or compressed, and which direction. And really, to be able to answer questions like these two, we would have to know whether any kind of stretch or compression was identified to be vertical, as it was in this first one, because they give us the general form with the A in it, or whether it would be a horizontal stretch or compression, which would then give you the general form with the 1/b in it. So you'll know, because they'll have to give you that. Otherwise, it's kind of, sometimes it's hard to tell whether something, because if you compress something horizontally, it looks like you're stretching it vertically as well. So it could go one way or the other. So they'll have to indicate if they want it to go one way or the other on that. So we're going to wrap up with just looking at some modeling with the f of x equals x cubed. So you may be able to model a real-world situation that involves volume with a cubic function. Remember, volume was like, for instance, a box. Length times width times height. You're multiplying 3 dimensions. You know how your units were, like, say, cubic inches, cubic centimeters, or whatever. Or you may remember, like, the formula for, like, a cylinder was pi r cubed. Actually, it was pi r squared h. Excuse me, I just said that wrong. I was thinking of the sphere when I said that. So it would be, we have pi r cubed h, but then there's basically, like, say, 3 dimensions that are multiplied. So it's a cubic function, because we have, 3, like a length, a width, and a height, let's say, that we're multiplying. So those are cubic functions. Sometimes mass may also be involved in the problem. Mass and volume are related through density, which is defined as an object's mass per unit volume. If an object has mass m and volume v, then its density d is equal to m over v. I just wrote that a little bigger. You may have seen that before in science, right? Density equals mass over volume. You can rewrite the formula as, we're going to write it as M is equal to D times V. So the mass is equal to the density times the volume. And more often, we're going to be using it in this format. So both of these are equivalent formulas, and we're going to apply this new one here, this new version of it, in our problems, our real-world problems here. So it says use a cubic function to model the situation and graph the function using calculated values of the function. Then use the graph to obtain the indicated estimate. So it says estimate the length of an edge of a child's alphabet block, a cube, that has a mass of 23 grams and is made from oak with a density of 0.72 grams per cubic centimeter. So first of all, you have to remember the formula for volume of a cube. Now you may just have always used the box formula, which would be length times width times height, right? But in a cube, all the dimensions, the length, the width, and the height are always the same, right? So if we called them all instead L, then our formula would be L times L times L, or L cubed. And that's what they have listed here. So L cubed would be the volume of that cube, right? So again, because mass is equal to density times volume, we could rewrite this specific problem as the mass, which is, they said was 23, that's the M, right? We know that this is the density, D. So if we substitute those things in, we would know that the mass, which is 23, is equal to the density, which is 0.72, times the volume, which is the length of the edge cubed. Now, one way to solve this problem is to consider a graph. Like you could take this side, this 0.72 L cubed, and you could graph it, and that's what they did here, okay? And notice they only, this doesn't look like a cubic graph, like it looks part of a quadratic, but the other side is over here, and the reason why we don't show it is it doesn't make, yeah, that doesn't look like that, more like this, is it doesn't really make sense for this situation to have negative, input values or negative output values, because you'd be saying negative edge length and negative volume, right? That can't be the case. So it's just the points on the right-hand side. So basically, taking those points that are positive for an x cubed function and applying this transformation to it, and then graphing this horizontal line at 23 and seeing where does it cross. Okay, and then that intersection point is the estimate of the length of the edge, right? So that's what they did here. They just took, made a table of values, and they just substituted into the function 0.72 length cubed. So they just kind of put some kind of standard lengths in, like 0 centimeters, 1 centimeter, 2 centimeters, and they just substituted these into this function right there, right? And they got these different outputs. And you can see the mass is starting to, as you go down, it's starting to get closer to 23, and eventually it goes past 23. So that we know it's got to be somewhere in this region right in there, right? It's got to be between 3 and 4. And so one thing that we could do is we could actually graph this on a graphing calculator, and we could see, to get a better approximation, instead of just looking at the graph here and saying, oh, it kind of looks like, okay, well, it's between 2 and, say, 3.5, it looks like. So maybe we guess, I gave an estimate of about 3.2 because it's between 3 and 3.5. Or we could use a graphing calculator to get a little more accurate value. So essentially what we do is we take the mass, and that's going to be a horizontal line, okay, and we could graph that, and then we could graph the density times the volume function, and then we can just see where they cross. Okay, so let's look at another one of these. So it says estimate the radius of a steel ball bearing with a mass of 75 grams and a density of 7.82. Let R represent the radius in centimeters of the ball bearing. The volume in cubic centimeters of the ball bearing is. Okay, so first of all, you got to remember that a ball bearing is like a sphere, right? So maybe you do, maybe you don't remember that the volume formula for, so you have to know this, the volume formula for a sphere is 4/3 pi, oops, I didn't leave enough space for that. It's 4/3 pi r cubed. Okay, so you'll have to know some basic geometry formulas. I don't know if that one's basic. I'd probably give you that one. And if we use that same idea that we said that the mass is equal to the density times the volume. So they said that the mass of this ball is 75 grams and that the density is 7.82 grams per cubic centimeter, but the volume is 4/3 pi r cubed. Okay, so actually all of this right here is just one constant number, right? If I multiplied those, they actually turn out to be, so 4/3 pi is about 4.18879, and then if you multiply that by 7.82, you get approximately, if I'm going to just simplify this for getting my coordinates, it makes it a little easier if I have it simplified. So that would be about 32.76 r cubed. So again, taking all these three things, multiplying them, I get 32.76 r cubed, and then that's supposed to be equal to 75. So again, to solve this, what we could do is graph this, and we could substitute in some different radii, like 0.5, 1, 1.52. So again, we could just plug these into this, figure out the outputs, and I just did it ahead of time. We're most likely going to use the graphing calculator on these anyway, but just if I wanted to do this by hand, I would plot, I plug in 0, which would give me 0. So obviously if the radius is 0, the volume is 0. And so with the mass. If I put in 0.5, I ended up getting 4.10. When I substitute in 1, I get 32.76, obviously because 1 cubed is still 1. Multiply that by that 32.76. If I substitute 1.5 in, I end up with 110.57, and I'm actually already past that 75, so if I wanted to stop, I could. I know it's going to have to be between 1 and 1.5, but I could also put in 2, and if I put in 2, it would be 262.08. And so I'm just going to go ahead and plot these. So 0, 0, a half, so these are scaled by, looks like 0.25, so a half, and 4, which is way low right here. That's way too high. It's way, way low here because these are scaled by 30s. When I substitute in 1, I get 32, so that's just above 30 right here. When I substitute in 1.5, I got to 110, so that would be right about here. And this is what my graph, see, this is why we wouldn't really do these this way, because, I mean, how accurate is this, right? And then, well, I guess we could put that final point on if we wanted to, 2, and it was 262, so that would be like right up here. Looks like this. And then we would plot this line at 75, which is about, oops, right about halfway between 60 and 90, right there. And that intersection point right there would be what the radius would have to be. So if you kind of guesstimate it, looks like it's a little past 1.25, but if I used a graphing calculator to figure that out, by graphing, say, in y sub 1, graphing 75, and in y sub 2, graphing that 32.76 r cubed, or x cubed, and then just see where the graphs intersect. So I'm going to do that right now. And so remember, to do the intersection, you go to second calculate and intersect. I wish I could show you this right now. But when I graph it, I'm not even really going to see, and I can show you this when we meet in class, but I'm not really actually going to see that line at 75 because my window is set up at a kind of a weird spot. So I actually have to change my window so that, which just means I'm going to have to go to the mode, actually not the mode, the window key, which is right next to y equals, and I'm going to change it so that my y max is past 75. So maybe I go to like 100. Then I can actually see where the graphs cross, and I'll take a picture of what that looks like here. So then all I have to do is just do my second calculate intersection and see where they cross. And I did that, and I can see, according to the calculator, they cross when x is about 1.32. So that means my r, my radius is about 1.32 centimeters. Okay. So if I were to take 1.3, oops, I said 3.2 and I wrote 3.1. Because it's 1.3179, so sorry, it's 3.2. So if I were to take that 1.32 and substitute it in for the radius, I would get approximately 75 for the mass. So again, I could plug it right in. Oops. Plug it right in here, and I would see that it would get approximately 75. That's about definitely closer than I can get trying to do some hand graph as I've done here. You know, my graph here was, I could see it was between 1.25 and 1.5, but that certainly is not as accurate as when I use the graphing calculator. So we're going to leave this one to do in class as just kind of another one to kind of wrap up. But just if you do want to try it, remember mass is equal to the density times the volume. So once you get this written, you can just separately graph 1 in y sub 1, that'll be your horizontal line, whichever the mass is, and then 1 in y sub 2, which is your density times your volume, and use just x for your unknown, right? And again, this is a cube again, so we use that same formula, that volume equals x cubed or L cubed, but we'll just use x when we use the graphing calculator. If you want to give that a try, and then calculate the length of the edge of the box. So that does it for today's class. Thanks for hanging in. I know this is a long lesson, so I'll see you in class.